All right, moving on, we are going to talk about graphical interpretation of average velocity. We can also analyze some various types of graphic representations of a particle motion. Here are some key issues, though, with this graph that's on the left. So it's kind of like, okay, they start at 1 meter from the origin. It looks like they're going in the positive direction, and then maybe they're like turning around and kind of increasing speed maybe as they're turning around and going the opposite direction. But it is kind of unclear on their actual speed. And I would also debate that it's a little unclear on direction at time. So we can fix this by making an X, meaning like where you're going versus T graph. Now, when you guys think of an X versus graph, you're probably naturally going to think X is on the horizontal axis, but we're calling position X. So it's like a Y versus X graph, except it's position, and they call position X and time T. So I know that's going to be kind of like, oh, I got to separate that from my mind. You can call an axis whatever you want. So I want my vertical axis, technically my y-axis, to be an x position and my time to be a t for time in seconds. So if you look at this one, it's actually really nice because we can see that like the speed is increasing. It's getting faster, but then like we're turning around, we're going down, and it's just a better representation of where you're at and your speed. And let me maybe explain this a little more. The slope of this graph between any 2 points is the average velocity. Now let's make sure that we highlight the word slope and we indicate that that's the average velocity. It's not necessarily the velocity at each and every moment, but it is the velocity overall for between any 2 points. So this fancy thing here is just saying like, okay, let's say you want the average velocity from A to B. Well, you find those 2 points and why don't we work it out? Okay. So let's do average. So if we start at A, so from A to B, position A to position B on this graph to B, let's find out what the average velocity is going to be. So I'm going to write them out as points, maybe 0, comma 1, meaning in 0 seconds, we're 1 meter away from the origin. And the other one's going to be 3, comma 2. In 3 seconds, we're 2 meters away from the origin. And that's just like by definition, like 2 points. Now let's go ahead and find that slope. So back to algebra class, set up my skeleton, 1 minus 2 and 0 minus 3, which is -1 over -3, which is 1/3, which, oh, this kills your math teacher. We're going to make into a decimal, zero point 0.3 repeating. Now, what is that? Well, that's your y-axis, which happens to be meters, over your x-axis, which happens to be seconds, which lo and behold, look guys, that's meters per second. So that is the average velocity, not the average speed, the average velocity. Let me see what else I have on my notes here that I want to teach you. Why don't we go ahead then and compare that with the average velocity here. Now what's cool, we can visually see that from A to B, overall, our velocity is positive. And if you look at the graph, you can see we're going up more than we're going down. But now let's take a look at this one from point A to point B. Let's call this new point A, new point B. So at different points. Let's see, that's at 2 and 4. I feel like I said let's see 4 different times there. I apologize. Let's see, point B is at 3, 2. Oops, look, I did it again. So we're talking about further in time now. So what we're going to do is to find our average velocity. Oh, I always do that wrong. Ready? Velocity average. There you go. Our average velocity is going to be calculated as 4 minus 2, finding my slope. My Algebra 1 skills are spot on, right? So are yours. 4 minus 2 is 2. 2 minus 3 is -1. -2. Oh, look, this time my average velocity, notice how I'm really stressing that out because we're going to learn about instantaneous later, is -2. And we know that because that green line is headed downhill. Now, is that the velocity at every moment? Nope, it sure isn't, but that's the average velocity for that particular time interval. In fact, I'm going to say from 2 seconds to 3 seconds because those are my I hate saying my x values. Those are my x-axis, my time values. So from 2 seconds to 3 seconds. All right. Now let's take a look at what else I have here for you. So this representation allows us to think as average slope, average velocity as a slope. And I've already discussed that. Please just remember, maybe right here in my head, I was like remembering the slope formula. Oh, look at that. I just did it wrong. Y2 minus Y1 over X2 minus X1. Just remember, it's whatever's on the vertical axis and whatever's on the horizontal axis. Okay? So I have an extra example here that I did not have, and what's really smart is I don't have an answer key beside me, but I feel pretty confident about this. So let's say we have this position time graph. It looks like we're um, going in the positive direction, right? Everybody see that? We're reading left to right, going in the positive direction from the origin, and then it looks like we're standing still. We're not walking, we're standing still. Our position's not moving. And then it looks like we're coming back we sure are coming back towards the original spot. So it'd be like, I'm going to walk, 50 feet away, and then I'm going to come back to the exact same original spot because you're actually ending in the same position. So from 0 to 0.5 seconds. So here's 0. 0.5, oh goody goody gumdrops. Let's take a look at this. So where's 0.5 at? That would be 0.6. 0.5 would be right there. All right, so those points would be 0, 0. I'm a point girl. Imagine that. I like math. I like seeing it worked out. To 0.5 and 0.5. So half a second, half a meter. So my slope's going to be delta x, which is the the change in position. That's so hard to think of, isn't it, guys? Because you want to think like delta x is this, but delta x is the change in position. So I'm just going to I'll do the second one minus the first one this time. So 0.5 minus 0 over the second one minus the first one, 0.5 minus 0, reduced is 1 meter per second. I ran out of room. Okay, let's do that again. Time interval from 0.5 to 1. So from here to ooh, that one's going to be easy. Does everybody see this flat line? That's definitely going to be a velocity, an average velocity of 0. But we knew that from algebra class. If you want to do like the 2 points, if you want to work them out, I guess that's going to be 0.5 comma 0.5 and 1 comma 0.5. You'll end up with 0. I know it's a straight line, so I'm going to write 0 meters a second because you're not moving. You're just standing there. It's like you're going to stand there for just a little bit, or maybe you're just busy turning around, right? Because it does take time to like turn around. And then we're going to come back towards the origin. So from 1 to 2, we're coming back towards the origin. Now, if you want to, this is at over 2 comma 0. So we can do our slope if we want. There'd be nothing wrong with that. I have a feeling it goes down one over one, down one over one, but I'm not sure. Let's see if we're right. It'll be fun. Okay, here I go. So that would be 0 minus 0.5 and 2 minus 1. Oh, silly me. That is not a slope of 1. That's because they're skipping by different things. Good thing I did my math. Negative 0.5 over 1, which is negative 0.5 meters per second. Da, 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 da. So, and that makes more sense, doesn't it? Because it's not quite as steep of a line. So you're walking, maybe you sprinted to a certain spot and then you turned around and walked back. All right. Um, what about, oh, look at this. What about 0.4 to 1.6? Oh, dear heavens. Here we go. You guys ready for this? Why not throw a challenge in there, Miss Langeli? So at zero point 0.4 seconds, let's see, where are they at? At 0.4 seconds, oh, that's hard to read, Langeli. It looks they're at 0.4 meters. At 0.4 seconds, it looks like they're at 0.4 meters. I hope you guys agree with me. And let's see, what's my other point? 1.6? Okay, 1.6, it appears as if they're at 0.2. Okay, so that was 1.6. It appears as if they are at, what did we just say? At 0.2. All right, let's do some math. So I'm just going to work into this page. That's That's going to show up weird. So I'll do zero point 0.4 minus zero point 0.2, and then I'll do 0.4 minus 1.6. So I get 0.2 divided by 0.4 minus 1.6, negative 1.2, divide 0.2 divided by negative 1.2, and I get negative 0.1667 meters per second. So when I connect those two dots, they better be looking like they're going downhill. You ready? Wow. And they sure do. So that slope just happens to be negative. And the reason like that's such a small number is because we had to accommodate for the fact that they went uphill, they stood still, and then they went downhill. So it's like that all gets taken into consideration in that particular average velocity. Let's see, what is this fun thing? I said let's see again. Boy, you guys must be annoyed with me. I may have used problems from here. Oh, open in Safari. It's an exciting time, guys. I sure did. If you need some extra problems, it would be worth your time. If you need to go through here and read this website, you can. All right, it was fun. First lesson done. Mark it off in the books.